Hello, everybody. Welcome to Global R&D of June 2023. Today we'll start with a community demo. This will be the Orally network who will present decentralized oracles that are fully on-chain. Then Stefan will present composite queries, a feature that many have waited for a long time. So I hope you get excited about that. Then we have a blog about features. They're all based around making ICP faster, more performant, and whatnot. So first, Alex will talk about how to increase throughput, or how throughput will be increased. Then Adam will present us wasn't stable memory, a way to use stable memory better. Then Luc will report on how now Motoko can use more memory because we have, hopefully will have a better garbage collector on the internet computer. Then we have another demo about around how to test an SNS setup. So if you want to launch an SNS, you want to test that beforehand, and Martin Darshaver will tell us all about that. And then we will conclude with a few announcements about some upcoming events and ask for participation there. So let's dive in and start with the demo, and I'll hand over here to the Orally network. Thank you.
Hi, thanks for introduction. Hello everyone, my name is Igor. I'm founder of Orally Network, and today I'm gonna describe what this Orally Network is and what this decentralized network is and how we can use it. So let me share my screen. So firstly, I want to say what is Orally is in general. So for our first two products, gonna provide fully decentralized data fetching from different sources, from different servers, aggregated and distribute to make a cost-efficient approach for distribution to different networks for different smart contracts. Another product is automation. So automation could trigger different contracts through various of chain and provide randomness and price feed from a previous product. So let's dive into a little details how it works. So Sibyl is our price feed oracle, efficient price feed oracle, which provides make decentralized fetching from exchange rate canister. Through exchange rate canister, it gets data from different forex data providers and centralized exchanges, aggregated, and we're getting from there, make a cache. So each pair has different expiration time and provide some CDCA signature. It's like a proof of exactly we fetch the data and sign it. So the user will be able to fetch from us this data as proof. Provided with a transaction to consumer contract, and this consumer contract will be able to verify correctness of the data and use this price feed for some business logic. And also we will be able to provide for different custom pairs rates, as users will be able to provide different endpoints where we need to fetch, make a decentralized fetch price feeds aggregated and like others list for users who need it. And next product is automation called Pitya. Pitya make automation for different chains. So it start timer which trigger 5 minutes, each 5 minutes. If we have a different subscription for different chains, we just execute a multi-call, one multi-call per different chain. If we exceed some limitation for the block, we do separate multi-calls for one chain, but in general, it just trigger when we need to execute some method in one of the chain, we set up it and send. So user can set up automation with randomness, pure automation without any type of data inside, and with data feed, which provided by Sibyl, by previous product. And it's just sending this multi-call, already predefined multi-call to preprocess, and it distributed to different chains. So yeah, I'm gonna show how Sibyl application, how our application works now. So we have just endpoint for which gets which make comfortable to get from gateway. For users will be able to just fetch our endpoint. It go to our canister, get go this method and provide pairs which they gonna fetch. So they get price feed and signature. With the signatures, they will be able to verify by our contract on destination networks and be sure that data is not compromised and they can use it. So in general, a verification method looks like a verification contract looks like this, and users will developers will be able just use interface of it and use verify method to be sure that data is correct. Yeah, so it's how our Sibyl works. So we just have predefined deployed contract with verifier, which user will be able to trigger to verify, and just a code how it could look like just a fetch, and they will be able to attach this data to contract. And our PTIA is for automation. So I'm gonna show you how automation works. I already have one user with predefined two subscription. One is for QChain, another one for Sepolia. And for example, as we can see, it triggers each 60 minutes this address, contract address with this method, and it provides a data feed. This provides randomness. And we need to top up a balance. Like we have one execution address which triggers its own multi-call, and users need to top up this execution address and provide transaction hash to be enabled to deposit account balance, and this balance will be this gas will be used for these executions. So we can see in this contract that we have a successful transaction 1 by hour or 1 by 1 hour, and it provides like this. So I need to change net, and it provides Ethereum data here. And our randomness will just provide a random number to this Sepolia chain to our contract by 1 hour. Okay, and let's create another one subscription to show how it works on GoAirly testnet. So we already have a predefined contract like that on the same address as a QMainnet. And right now there is the duplicated data of ICP price, and let's try to set up with Ethereum, for example, price. So this method is set price. We can see we need to provide gas limit and extra gas limit which did not use, just stay on the user balance and provide price feed. We already topped up a balance and we can just send subscription. So subscription created. And let's wait a little when it could be executed, because we have a timer which executes everything once per 5 minutes. So it could go in this time frame, and it could not show. But and also in general, I wanted to show that, for example, if we choose another wallet. For now, we maintain only whitelisted addresses. So if you will want to check that out, reach us out, and we will add your address as a whitelist, and you will be able to try to use it or set up some automation for your contracts. So yeah, we just need to write a bill for next execution. Yeah, a new round of all subscription execution started, and it's gonna execute this 3 subscription for different chains, different contracts. And for price feed, user will be able to, like with a Sibyl approach, they will be able to make a super gas efficient approach, because they won't need to make every 5 minutes or 1 hour execution to update price. They will be able to make their own system on the front end side to add this fetching this data with a proof, and update this data only when user will need the data to interact with. Yeah, it could take some time, because when we make we need for each transaction to fetch different data from the through the RPC about the blockchain, to combine the data, sign with ECDC signature, and send it to RPC and being executed on the chain. It's like increase by each chain added, it increase a little volume of different HTTP requests, but when we will cover all the chain, it will be we're already optimized with multi-calls on all the chains. So we can see for already 1 chain, Sepolia already executed, and we can see that randomness is updated on Sepolia contract. Also for our Guerri contract, it also should be updated soon. Yeah. Okay, I think that's all for me for now. Thank you for attention.
Thank you, Ihor. Very cool. Next up, we have the demo by Stefan about composite queries. And as you know, so far we couldn't really, like a query call could not call it to another canister. And well, this is going to change. Stefan, tell us more. Thanks.
Thanks, Jan. Hi, I'm Stefan from the runtime team, and today I'm going to talk to you about composite queries. And as Jan already mentioned, so far you can only do calls into other canisters from update calls. And this is something that we have been working for a while now, which is to bring calls also to queries. And the reason we do that is that it improves your latency, especially if you have multi-canister architectures. So your DApp is composed of multiple of those canisters, and you want to efficiently aggregate data from multiple of these. This is a pretty highly requested feature by the community. There has also been an NS proposal already that has been approved. And today I'm going to talk a little bit about what we have been doing to make this work. And what we had to do basically is to add a new type of query, which is called a composite query. And in that composite query, you can now do calls. Next slide, please. What I will show you today is a demo of like a toy example, which is a partitioned key value store. So what we do here is we hold pairs of key values, but we partition it. So there are multiple backends, 1, 2, 3 here on this slide. And there is a front end that knows where key value pairs should go based on a hash function on the key. And this is completely transparent from the user. So the user always just goes to the front end, and the front end manages the partitioning in the backends. Next slide, please. Here you can see an example of how this looks in the code. And for the ones of you that already have been writing some canister code in Rust, that will look very familiar. So in addition to the like macro that you put in front of the function that tells the system that is a query call, we now have this additional annotation that says that this is now a composite query call. Other than that, there isn't really anything super fancy in here. So for our toy example, we take the key that comes into the function as an argument, and we look up the partition for it, which gives us a canister ID. And then now we can do a call in this query, in this composite query. And that looks basically exactly the same as you would do from an update method. And with that, I would like to share my screen to show the demo. Can I share my screen, please? No. Thank you. Okay, so what you see here is basically 2 windows. In the top, we have the demo app already deployed to SDK instance that I have, DFX instance that I have been starting locally. And we have a front-end canister, which has this canister ID, and we have a set of back-end canister IDs, these 3 ones. And what I'm going to do now is I'm going to do a bunch of put operations and get operations on that. And I will mostly be talking directly to the front end. So let's put something into key value store. And you can see at the top that the front end has received that. It's looking up the canister ID that should be holding that key value pair. And it then does a call into this canister and puts the data here. So far, this isn't composite queries, right? This is an update call. So now let's query this value again. So now we do a get against the same key. And that now goes pretty quick. And we can see again at the output that we have been using the front end to look up what is the backend canister, and the backend has responded to this request. Of course, we can also put other things in other canisters, and you can see that this actually goes to a different canister. What we can also now do is we can also look up a canister ID responsible for a certain key. In that case, I'm just going to use one of the keys I just put, and it tells me which canister it is. And just to prove to you that this is actually working correctly, we can do a direct call into the backend as well. So I'm just taking now this canister ID that comes out from the front end, and we'll query directly against it. And we see that the same value comes out. And we can also verify in the output that, in fact, the expected backend canister has been responding to that call. And obviously, we can now also try to look up a key in a backend that doesn't have this value. maybe we use this one. And then that should not work, right? So that's basically a proof that the data is where it's supposed to be. And just for a comparison in terms of latency, so if we would now implement this get that we have here, which is now in this demo using the composite query feature and has a pretty good latency, right? This is clearly sub-second latency. We could obviously also do it the old way and just do an update call instead. And that is obviously significantly slower because executing this as an update call needs to go through consensus, although we're not changing any states. So we can see here that using the composite query feature, we can get a significantly better latency for read requests into our DF. And with that, I would like to go back to the slides. We also have some limitations for now. Those are that currently the composite query calls, they can not go across subnets. And if you annotate a function or you specify a composite query function, you can also not execute that function in replicated mode. So that means you cannot execute a composite query call as an update call. These are possibly temporary restrictions. We are still looking into those, but we thought it's already worth rolling out this feature as it is now because we think there's already value in it. And here you can see what sort of calls are allowed. So for an update call, you can obviously call into another update function and into a query function. And from a composite query call, you can do a call into a query function and also in a composite query function. If you want to know more about that, we have a lot more technical details in one of the previous global R&Ds that I have been linking behind this QR code here. Next slide, please. The current status is as follows. The replica changes have all been added to the code, but they're still behind a feature flag. We are now planning to release code or put up code for Vote soon that has the release, the bit flipped so that you can use this feature. The Rust CDK support is completed. Candid support is completed and merged, but not yet released. We have Agent.js and Motorcore, which are still in review, but they should be ready soon as well. We even already have ASIL support, which makes us very happy, or I should probably say preliminary support. And there is, of course, the code from this demo, which you can all have a look at. It's linked from this QR code on the right. When all of this is done, we are planning to also do a blog post, so you know when you're ready to go. I wanted to say a big thanks to everybody who helped with that. We have a lot of people from within DFINITY, from different teams that helped with that. And we are especially happy that the Merchant Labs is already working on ASIL support. That's it from me. Back to you, Jan. Thank you.
Thank you, Stefan, and to everybody who was involved here. And I'm really looking forward to read that blog post. So yeah, let's continue with the improvements that the Internet Computer will see, and start with throughput increases that are caused by file-backed allocator. So here, Alex, please explain what the heck file-backed allocator are and how they help to improve the Internet Computer.
Yeah, thank you very much, Jan. Hello, everyone. I'm Alex. I'm a researcher in the runtime team. And yeah, I'm very happy to talk to you today about the throughput increase that the IC can actually have from now on. And this is due to the file-backed allocator. But let me actually start with a bit of context. So at the moment, the hardware of the IC has 32 cores or 64 hyperthreads. But during message execution, the nodes actually use only 4 cores for updates and 2 calls for queries. And ideally, for the IC community, this throughput would increase. And the way to actually do that is through this file-backed allocator that allows growth. And I'll talk a bit why on the next slide. So I think, you know, the throughput increase, we don't need to talk much about because, you know, the IC, it's seeing increasing workloads, so it will need to up its game. But for the file-backed allocator, basically, the reasoning behind it is that most of the IC replica data structures are stored in memory. So in the worst case scenario, nodes can actually only fit 4 update and 2 query canisters. And then the memory space will actually get filled. So it would be kind of difficult to increase throughput without making some headroom for new canisters. And I'll tell you how into the next few slides. But let me actually start with a short recap. So whenever someone develops a canister, that canister will be compiled and translated into a WASM binary, which has some state, which is this, let's say, checkpoint file at the right here. And then whenever this WASM binary runs instructions, some of these instructions will actually read or write some of this state, this memory. This memory is split into pages. And well, for all the reads from an unaltered state, they will just be fetched from this checkpoint file. Whenever the canister alters its state through writes, there's this data structure called the heap delta or the page delta that keeps track of all the changes that the canister takes during a checkpoint interval. After the checkpoint interval is done, what happens is that this data structure gets flattened and written back into the checkpoint file. Now, the idea behind this heap delta or page delta data structure is that it's only in memory. And for all the canisters actually running in a subnet, it can only be 150 gigabytes per checkpointing interval. And yeah, this basically occupies a lot of space and doesn't allow, let's say, more canisters to run. So that's why we cannot increase throughput. So ideally, we can free some of this space up to enable the IC nodes to run more canisters concurrently. And I'll show you how on the next slide. So what happens is that we can back these page deltas by means of on-disk files. So whenever there's something that's written in memory, we will also mirror it on disk. So all the changes will happen in both places. And then when memory will be scarce overall, so there's memory pressure, there's many things happening. What happens is that the node can actually drop this data from memory because it's still on disk and we'll just keep it there. Yeah. And then this is the main idea behind this feature. Of course, there's lots of technical details that happen, but I'm not going to dive too much deeper into that. But on the next slide, I'm going to talk a bit about the status of this feature. So initially, because this is quite a sensitive part of the system, we propose to carefully release this allocator. So by now, it's for about 2 weeks or a bit more than 2 weeks only on application subnets. And I'm very happy to say that there's been no hiccups. So things are working just fine. And for the last week, we also propose to actually double the number of query threads for the same application subnets. And this is also working just fine. And then in the future, we will propose to actually roll out slowly this entire thing. So both the file back allocator and doubling the number of query threads to all of the subnets. And then in the next iteration, if the community wants this and likes the feature, we can propose to double the number of update threads as well. So on the next slide, I will show you some results. So basically, you're going to ask, okay, you're writing more data to the disk. Are there any consequences? Well, there's no bad consequences. So the problem behind writing more data to the disk is that perhaps we would interfere with other components that are writing data to the disk as well. And in our case, the checkpointing is one of these components. So what I am showing here in this graph is basically the checkpointing performance before and after the file back allocator was deployed. And yeah, good news, nothing has happened. So this is good. So there have been no slowdowns. Now, let me show you even the better side. So on the next slide, all the canisters, when they receive queries, they have a queue to store these queries until they are able to get executed. So what I'm showing here in this graph is basically a before and after story. So when we had 2 query threads, these queues were larger, and it meant that the queries were there longer. So the people waiting for these queries had to wait longer. But then after the 4 query threads were deployed, the queues were longer. So that meant less waiting time. But it's kind of difficult to quantify with this kind of data. By the way, this is production data, mainnet. What the benefits could be overall. So on the next slide, I will show you some other experiment where I will try to convince you that this feature actually is able to double throughput because we double the number of execution units for queries. So there's 3 workloads that I focused on our testnets. So we have short queries that basically are not doing much, but they are very, very short, like a few milliseconds. So they are latency bound. We have memory intensive queries and CPU intensive queries. So they are longer and do different things. So one touch is memory and the other one does a lot of CPU intensive operations. And for all of them, the improvement is very good. So for the short queries, it's like 1.75. But for the other types, it's almost double. So this is really, really exciting news. The IC is now able to run workloads faster or more workloads. So I invite you all to run your workloads on the IC and see the difference. That's all from me. Thank you very much.
Thank you, Alex. This is super cool. Well, next on we have Adam, who will tell us about WASM native stable memory and tell us how cool that is.
Hi, everyone. My name's Adam. I'm also a developer on the runtime team with Alex. And yeah, I'm going to talk about WASM native stable memory, which we've been working on for a while. And so this is basically just a performance improvement to stable memory. So it doesn't require any changes from Canister developers. It's just a pure benefit that you should see if you're using stable memory. So why are we doing this? Well, I mean, who doesn't like improved performance? It'll just make canisters run faster and more efficiently. But it also unlocks some things. So it makes it more realistic to use stable memory for your permanent data storage. And that allows you to either vertically scale a canister better or to perform safer upgrades by not having as much code in your pre and post upgrade hooks, or maybe having almost no code there at all. So how is this done? Well, the basic idea is that we handle the stable memory API calls purely within WASM code. Previously, these APIs had to go through our WASM runtime and into some replica code, and there's a whole context switch there that goes on, which we can avoid by handling it all purely in WASM. So that's the basic idea. Next slide, please. So here's a link to the proposal on the forum from a few months ago when it was this idea was originally discussed. It has some more details of the design, but nothing has really been changed since then. It's still the same basic idea. Next slide, please. So I'm just going to describe a bit more about the design now. So as I said before, the stable memory API calls have to go through the runtime, and that's what we have pictured on the left. That's the original design of the stable memory API. So in the blue dotted line, this is our WASM code that has been compiled to x86 instructions. And when the canister needs to access the regular memory, that essentially is just an x86 load or store instruction to read or write to main memory. But when the canister wants to access the stable memory, it has to do this function call into the runtime, and then the runtime has normal access to stable memory through standard x86 instructions, but it has to get those values back, and then it has to return them to the canister. And these calls through the runtime are what add a bit of overhead. So on the right side, we have the new design under WASM native stable memory, where the access to the main memory and the stable memory are essentially the same, in that your canister code gets compiled to x86, and any reads or writes from main memory and stable memory should essentially be just regular x86 load and store instructions. No extra function calls involved. There is some extra overhead still with stable memory. We have to do some bounds checking on the axes and things like that, but the core logic is that it's just a regular load or store instruction, and that's what makes it faster. Next slide, please. So here's a summary of the performance changes based on some benchmarks. So I have two tables here. The left shows some benchmarks that directly call the stable memory APIs. And on the right, I have some benchmarks that are using a library, in this case, the IC stable structures library. But ideally, results should be similar for IC stable memory as well. So on the left side, you can see that a handful of these benchmarks are faster. Some don't have much change, and one is a little bit slower, which is something we still need to look into a bit. But you can see the key things are the reads, like small reads are generally faster, and sparse writes, small sparse writes are generally faster. Like reading a large chunk at once or writing a large chunk at once don't see significant change. So that's pretty good. So this shouldn't have any performance hit to something that's just like serving large data directly out of stable memory. But on the right side, you can see that basically everything that's using a library gets significant speed up. And that's because when you're using, for example, like a B tree and IC stable structures, you're going to do a lot of small reads kind of no matter what you're doing with the tree, because you're going to have to traverse through the tree to get to different points of data that you want to access. And so the fact that these small sparse reads and also small nearby reads get a big performance improvement sort of means that no matter what you're doing with like a B tree or a VEC and stable memory, you're going to get that speed up. So most of these things are like 1.5 or 2 times faster. Next slide, please. So here are just some examples of the benchmarks. These are the direct axes that are reading things. So on the left, we have many small reads near each other. In the middle, we have more sparse reads. Doesn't see as much of an improvement. And on the right side, we have a single read of a very large region, which is about the same. Next slide, please. This is similar to writes. So like small sparse writes have a big improvement. Repeated writes to the same region are a bit slower, but the error bars are also kind of large there. And writing a larger chunk is pretty much about the same. Next slide, please. And so here's an example of some things using the IC stable structures library. These are various operations with a B tree, and you can see that everything is pretty much like 30% to 50% better. Next slide, please. Yeah, so the proposal to actually enable this has been up and approved by the community, and so the community is currently approving proposals to roll this out to all subnets as we speak this week. So by next week, no matter what subnet you're on, if you're using stable memory, you should see some performance improvements from this. And that's all.
Thank you, Adam. Well, let's just finish with this global R&D before we all head over to vote on this cool new feature. And yeah, let's give the floor to Luc, who will tell us how much Motoko has become better.
Thank you. My name is Luc. I'm a software engineer in the Motoko language team and happy to announce a new garbage collector. That's the most advanced garbage collector for Motoko. It's an incremental garbage collector with one and only goal, scalability. The idea is that programmers can use the full heap space. On the next slide, we see a little bit what the problem is. Like classical garbage collectors, also like all the existing garbage collectors in Motoko, they need to occasionally interrupt the application, but then the garbage collection needs to run in one go. And this can, of course, then be problematic if the garbage collection can take a long time and it can exceed the instruction limit. On the other hand, the incremental GC splits the garbage collection work in multiple short work steps, and the application can run in between. If we go to the next slide, I charted the heap size with a benchmark application that allocates continuously objects and inserts them in data structure, and also creates a certain amount of garbage. And we see here that the current garbage collected fails at about 900 megabytes because it exceeds the instruction limit. On the other hand, the incremental GC is able to scale to the full 4 gigabytes of memory space. If we go to the next slide, I have a little bit more results out of the benchmark. The garbage collection benchmark, these are average results of all benchmark cases. We see, as expected, the usable heap size has been extended. Like, we can now use nearly the full 4 gigabyte heap space with some reserve for the garbage collection structures. Also, a nice thing is that the garbage collector is the fastest one among all the garbage collectors in Motoko. It's like a performance increase of about 10% on average. It comes with a moderate overhead in memory, like the memory footprint is a little bit higher by about 9%, which I think is acceptable. On the next slide, I would like to explain a little bit how the design of the garbage collector works. It runs in 3 phases, all incremental. The first phase is marking, then comes evacuation, and finally updating. We'll explain those phases in more detail later on. The garbage collector works on a heap that is logically partitioned in 32 megabyte sections. Several of these sections can be used, partitions can be allocated. One is used for performing the current allocations, and the other partitions are free. If we go to the next slide, we see how the marking phase, it illustrates the marking phase. The idea of the marking phase is to figure out all the live objects by transitively traversing through all the pointers, direct and indirect pointers, that are coming from the anchors from the root set. And in this slide, like these dark colored rectangles, they denote the marked object. This phase runs incremental, meaning that the program application can continue to run, and the marking phase has a special scheme that can handle concurrent pointer writes and allocations, which are critical to catch by the garbage collector. On the next slide, we see then the next phase, that's the evacuation phase. The idea of that phase is that it focuses on the partitions with a high amount of garbage. And that's also the reason why the garbage collector is particularly efficient, why it's the most efficient garbage collector. And what it does, those selected partitions, it copies the live objects into a fresh partition that affects at the same time compaction of the heap. Also, this phase runs incremental. If we go to the next slide, we see that the application may still continue to use pointers that lead to old, like objects at the old locations, but this is no problem because the old locations has a forwarding pointer installed that leads to the new location, and then a program application can follow that forwarding pointer to reach the recent and right version. And then on the next slide comes the final phase of the garbage collector, that's the updating phase. The garbage collector goes through the heap and sanitizes all pointers that have referred to an old location in order that they now point to the right new locations. Once that is done, the evacuated partitions can be freed, and that free space can be recycled for new allocation. On the next slide, I would now like to invite you to try out the new incremental garbage collector. It's hidden still like behind a feature flag, --incremental-GC. Feedback is highly welcome. And we plan then after some time to enable the garbage collector as the default garbage collector in Motoko. I would like to thank Claudia and Ulan for the review and contribution of ideas. And the incremental garbage collector has also a nice feature that it is able to scale also beyond 4 gigabyte. And that's the plan, like for next step for Motoko, to go to 64-bit and also offer like a nice approach of enabling scalable upgrades by moving the heap into the stable memory. And with that said, I'm handing back to you, Jan.
Thanks, Luc, Claudio, and Ulan for this great work. Right, so as you see or probably have seen, like currently Hot or Not is is about to launch an SNS, and about the fourth project now, and so for enable other projects to do it much easier, we spent some time also based on feedback from these projects, such Hoddernaut and the Kinnig and so forth, and how to get towards launching an SNS. And so the crucial step here is, of course, you want to test run that. You don't want to just get your DApp decentralized and then suddenly get your life much harder. And therefore, you need to somehow test that. And Arshavir and Martin will tell us much more on how to do that. Over to you, Arshavir.
Thanks, Jan. May I share my screen, please? I'm Arshavir from the NNS team, and I'm about to present NNS testing. This is a Docker-based solution that allows you to bootstrap a local environment for testing SNS decentralizations of your upcoming dApps. And the purpose of it is to launch with more confidence, as mentioned by Jan, but also to iterate and fine-tune the parameters of your SNS. And of course, it helps familiarize developers with SNS on a slightly more technical level. Before I jump into the demo, a quick disclaimer is that this is not a new product that DFINITY is offering, but rather it's a starting point that allows you to easier bootstrap an environment and then adapt it to your own SNS testing use case. So if in doubt, please refer to the documentation of our official SDK tools such as DFX and Quill. Now, before jumping into the terminal, let me give you a high-level overview of the architecture of the system that we're about to bootstrap. We assume that there's a host system, that's the orange box, and you have your dApp that you want to decentralize. Now, SNS testing is a Docker-based solution, as mentioned. So when you start the SNS testing Docker container, you need to mount the project directory into it. The home/SNS directory contains all the scripts needed for bootstrapping and operating an SNS on this local environment. And in particular, you can deploy a new SNS to start a local replica instance inside this Docker container. And then you can use your normal deployment scripts to deploy your dApp onto the same DFX local replica instance. However, you can also use a web browser as normally on your host machine to interact with the same system. And this is possible because we're forwarding the right ports from the SNS testing Docker container. And in particular, this allows you to manually participate in the SNS swap. However, for certain testing scenarios, you also want to be able to script the participation of multiple users and not do that work manually. And for that, we also provide special scripts in SNS testing. Now it's time to demo, and I will start by showing you the structure of the README file. In the root of the SNS testing repo, you will see all the instructions in this file that you need to work with SNS testing. In the preamble, we explain the purpose, and you can see what these instructions cover. And the first technical section is addressed to Apple Silicon users. But for the purposes of this demo, I will jump to the next section, which is focusing on users of all other platforms who can use Docker directly on their system. And I am going to open two terminals to go through the steps of the instructions. And as mentioned, we assume in SNS testing that there already exists a project to be decentralized. So to create such a project, I just use a DFX new command and call the canister my_dApp, for simplicity, not asking for a front end. And if you look into the dfx.json file that has been generated, and at the top, you see that the canister is actually called my_dApp_backend. And this is the one that in this demo, I will use to demonstrate how SNS testing works. Also navigating to the same place in the bottom terminal. And now I can proceed with the second step, which is this big command that will run a local replica instance inside the Docker container. This will, when run for the first time, pull the SNS testing Docker image, but I already have that. And as soon as you see the dashboard URL, that means that the local replica has successfully started. So the next command that I'm running is the setup locally.sh script inside the container instance. And this will be the last preparatory step needed before we can start the decentralization testing. While this is running, and it will take about a minute, let me say a few more words about the README file. So here, step 4 is a non-interactive script called run basic scenario.sh. If you run this, it will allow you to go through all the lifecycle phases of an SNS and thereby validate that SNS testing is working end-to-end on your host system. But for the purposes of this demo, I'm going to skip that step and jump to step 5. And in this step, in order to execute it in both terminals, I will need to export the SNS testing instance variable. And as soon as the command in the upper terminal is exited, I can copy and paste the corresponding instance identifier. So we have proposal 3. We're expecting 8 proposals, which are adding the SNS canisters to the so-called SNS WASM canister. 7 and 8. Okay, and now I just need to copy this and paste it in the terminal below, after which I can enter the Docker container from both of the terminals. And in the bottom terminal, I'm going to navigate to the /dap directory where we have our project mounted. And this is the project that we will decentralize. Next up, we jump to the section that covers the SNS lifecycle. And it starts with executing this cleanup step, which won't do much in this case because the file system is already in the good state, but never hurts. And in the first step, we need to deploy our DApp to the local replica instance that is currently running. And to do this, I'm going to use dfx deploy my DApp backend -- no wallet. And you might have your own scripts for running the deployment. But if you don't have your DApp, you can still follow these instructions because SNS testing comes with an example DApp built in. And this is what would happen if you run the example command listed here. Okay, and now that the deployment has succeeded, I can also print the identifier of my newly deployed canister. And now we're ready to deploy the SNS, and we need to decide which SNS test.yaml configuration file we will use. You can open this file and see what test configuration we ship with SNS testing, and most likely you will need to adjust this for your own project. It includes parameters such as the name of the token and other interesting parameters as well. So this command is expected to take also about a minute. While this is running, let me explain what the following steps will be. So we need to run the deploy SNS.sh and pass, sorry, this one I already did. We need to register our DApp using the identifier of the canister below with the SNS. And for that, we have a snsdap.sh script that performs this. Then the optional fourth step is to test upgradability, and we will skip this in this demo. And finally, we can open the SNS swap by running opensnsswap.sh. After this script is completed, I can now open my web browser and navigate to the Launchpad. Here, if I create a new test anchor, fill out the mock captcha, which is only so simple on a testnet. You can also press the Get ICP button. Unfortunately, not available on the mainnet. and I can participate. And let's say you want to participate with 4 ICP. All right, this worked. But what if, as I mentioned before, you want to participate or model the participation of multiple users? Well, that's where the participant SNS swap.sh script comes in. So here I can model 3 users per 10 ICP. And we should be able to see their contributions popping up almost in real time in the NNS step frontend. All right, so we got the maximal possible participation for this SNS, 30 ICP that we configured in our example YAML file. And that means that we don't have to wait until the deadline is reached to be able to finalize the SNS. Recall that before finalizing, the decentralization did not yet happen. So to finalize, we're calling the finalize SNS swap.sh. And if I refresh the page in the front end, we will observe that the status is now switched to completed. And if I navigate to my neuron staking, there's my testnet token with a test neuron basket that I can see. So with this, I will conclude the demo, and a big shout out to Martin, who was the main creator of the SNS testing solution. Thank you. Back to you, Jan.
Thanks, Arthur, Martin. I'm sure a lot of projects that are going towards SNSs are really grateful for this. Thanks a lot. Yeah, let's wrap this up with a few announcements that will come after. Yeah, here. Well, first of all, huge congrats to the Helix team who won the Crypto Valley Conference 2023 award. So it's really great to see like projects, ICP projects getting prizes. Really great. Thanks a lot. I'm not sure whether you guys are on the call or not. Yeah, so let's go to the next event and see how other people can get some awards for their work. And in particular, the hackathon around Bitcoin is wrapping up, and we have the finalize and prize giving away event next Wednesday. So here's the code for registering. Please register and see who else is getting prizes. And the next event that we would like to announce is the ICP Lab in the fall, in September 11th to 14th at the headquarters here of DFINITY in Zurich. And this will be about gaming and metaverse. Also, here is a link. Please apply before July 7th. So you have still some time, but not too much, about a week and 2 days to register here. And while we're talking about events, on the next slide, there's a quick summary of some of the events that the DFINITY Foundation people will be present. So this will be Lugano, East Barcelona, and East Paris. So reach out, let's meet up there if you guys are also going. And yeah, let's talk all things ICP there. With that, let's wrap up the last slide. So thanks a lot for attending. And also I would want to announce that this will be the last one that event that we streamed live on YouTube. So in the future, we will not stream live on YouTube anymore, because that has turned out to be a bit too complex to handle. So we want to keep things a bit simpler, and we'll just move back to Zoom only, and then instead put the recordings on YouTube later on. So thanks for all of that. And with that, yeah, share your feedback on the forum as well about the Global R&D. The forum exists since a while, and we've gotten good feedback there already. So please go to the forum if you have still some time or in the future, and otherwise see you soon again on another Global R&D. Thank you. Bye-bye.